This is our first chemistry class done via video. Hopefully we can get this to work out. So we will be continuing our class starting on page 182 in your textbook, continuing the study of selected metals and their uses and how we get them. Our last class we finished the first few metals, so we are on chapter 11.4, and we're going to be studying iron today. So iron is the fourth most abundant element on the earth, and it's the second most abundant metal. So iron is this one right here. It has the symbol Fe. And it's being the second most abundant metal on the earth. The only one that's more abundant is aluminum, but iron is much cheaper to get from ore and is much more widely used in the form of steel. If you look on page 182, there's figure 11.8 that shows an iron ore mine. So how do we get iron? Iron is, we get it by mining the ore like it shows in that photograph, and then it is brought to a blast furnace. And I'm going to draw you a picture of a general concept of what a blast furnace looks like. So this blast furnace is coated with fire-resistant brick, and right here is where fumes are piped out. Right here is where all of the ore and the parts that we mix in to make the metal are dumped in. It's mostly iron ore, coke, and limestone are poured down in here where the fire is burning, and then in the side here is pumped in pure O2, pure oxygen or preheated oxygen is pumped into the side here to keep a big fire burning in here with all of the coke, the iron ore, and the limestone. And as it melts, it comes down here, and off here goes the iron, and it's dropped into some kind of casting. The stuff over here floats off the top here is the slag. Now, I don't know if you remember a couple of chapters ago I mentioned coke and what coke was. Coke is coal that they have heated up hot enough to burn, but there's no oxygen so that it doesn't burn. It's the closest thing you probably can relate it to is charcoal. In fact, in the old days, back in the 1800s with steel manufacturing, it was actual charcoal instead of coke. But coke's easier to get nowadays with the coal mines, and so that's where we get most of that. This slag is made up of, the reason why we put the limestone in is it collects with all of the other impurities, or most of the other impurities, and binds to it, and it's lighter than the steel, and so it flows off the top. And so we get pure iron over here, or really close to pure iron over there, and we get slag that comes off of this way. This is called a blast furnace. And the iron that's poured in over here is put into casts, and it's known as pig iron also. mostly because of the way the castings look. It looks kind of a little bit like a pig with a couple of legs and stuff on it. But so pig iron has some carbon that comes out of the coke process. It actually has a lot of carbon in it. So pig iron has 4 to 5% carbon in it. And it makes it really brittle. And so if you've ever heard of cast iron, like cast iron pans, the cast iron sounding board on a piano or things like that, or it's not just a sounding board, but the harp that holds the wires in the piano, those are made out of cast iron. It's pretty brittle because it has a pretty high content of carbon in it. One thing also to note about the blast furnace is in the United States, in the past, almost all steel was made using this blast furnace form of steel manufacturing. But as coke has got harder and harder to get because environmentalists and that don't want us to dig up the ground and disturb the nature and things, it's getting harder and harder to get coke. And a long time ago, it got harder to get trees, so they couldn't do the charcoal. So there's some other ways that we get it nowadays, and we'll talk a little bit more about some of those other ways a little bit farther down. Actually, I guess I'm going to talk about it right now. Sorry about that. One of the newest ways of reducing iron is a natural gas production system, and it creates instead of getting pig iron, you get what's called sponge iron, which is has different purity levels, and some of the modern systems use that. But the one that the United States historically used, I don't think any of you guys remember Geneva Steel, but Geneva Steel had these great big tall blast furnaces that were maybe 15, 20 stories tall. They're really big blast furnace systems. So the most used form of iron that we have in the United States is steel. And there are many different types of steel. Carbon steel is the most popular use for steel. 90% of all steel is carbon steel. So carbon steel has a certain percentage of carbon, but we do things to it to make it so that it has less carbon than cast iron. So when you go through purification processes and clean up the steel, if steel has about 0.1 to 0.2% carbon, then that is called mild steel. Mild steel is used for all kinds of things like pipe, wire. Those are the two of the most common uses for mild steel. And then you've got medium steel, which would be 0.2 to 0.6% carbon. So it has more carbon than mild steel, but it's still not super hard. Medium steel is stuff that we use, it's stronger, and it's usually for structural steel. When you think of Brian's welding shop and the I-beams, or these tall high-rise buildings that are in big cities, rail lines, the tracks on railroads and things like that, those are made out of medium steel. It's not brittle, but it's still extremely strong. And then the next type of steel is called high carbon steel. And high carbon steel has 0.6 to 1.5 carbon, and this is going to be called high carbon steel. Now, high carbon steel you're probably familiar with. If you've ever used knives or things like that, it's a real popular use for high carbon steel. Tools, drill bits, all of those things use high carbon steel. Now, you'll notice that at 1.5%, that's still a lot lower carbon content than cast iron. Cast iron still has a really high carbon content, and that's one of the reasons why it breaks really easy. If you were to take a frying pan that's a cast iron frying pan and hit it really hard with a rock, it would probably just break, not bend. It doesn't bend very well at all. So now 90% of all of the steel in the United States is some form of carbon steel. The other 10% is made up of alloy steels. And alloy steels use other metals to change the steel's characteristics, improve some of its resistances to different things. And alloy steels usually have about 1% to 5% of some other metal. So an alloy steel will have 1 to 5% some type of other metal. So high percent alloys will be even sometimes more than 5% if it's considered a high alloy steel. Now, some types of characteristics of some alloy steels would be things such as stainless steel. Stainless steel is much more corrosion resistant. It doesn't rust, and sometimes is even resistant to some types of acids and things much more so than regular carbon steel is. And it's considered a high alloy steel because it will have as much as 14 to 18% chromium and 7 to 9% nickel. And if we look on page 184 on table 11.5, there's a list there in your book of some of the properties of different alloy steels. So if you look at the first one, it says vanadium steel. It has a springiness and a tensile strength, which means it can flex more without breaking. Magnesium steel is very wear resistant and is really hard for certain types of special bearings and things like that. You have chromium steel is very hard and corrosive resistant. Nickel steel is just tough and strong, so it's not going to break as easily. And then you have tungsten and molybdenum steels that are heat resistant, and they're strong and tough as well. So those are a few of some of the more common forms of alloy steel. On page 185 at the top left side, you see what's called a basic oxygen furnace. And that's where the steel, the rough steel, is sent after the blast furnace that we already talked about to pump a lot more oxygen into it and help to purify it and burn off some of the excess carbon that made it too brittle. And right next to it on the right-hand side of that same page 185 is an electric arc furnace. And some steels now manufacturing, they use high current electricity to get it really, really hot and to help purify the steel also. Now, right now in the United States, about 60% of the steel in the United States, the purification process is done with this electric arc furnace to purify it. And that brings us to how to prepare steel for its use once you've made the actual steel compounds, how do we work with it to make it usable? And there's a few terms here you're going to need to understand. And here again, this first one's on page 185. Annealing. The annealing process is that you heat it up and then allow it to cool slowly over a long period of time, like several hours, so that it takes all the stress out of metal. Because when you manufacture steel, it's going to have stress built into it. And by heating it up, it allows it to just kind of relax and puddle, takes all the stress out of it, and you allow it to cool slowly. And then after the annealing process, it's softer than you usually want it. And so then you have to take it through a process of doing some kind of hardening. And historically, the way hardening was done was through like blacksmithing. You take a relatively softer steel and you heat it up to about 700 to 800 degrees Celsius, about 300 degrees Celsius, and then you pound on it with a hammer, or historically there would be stamping where they'd have hydraulic type hammers that would stamp it and compress it. And they even have what they call cold rolling, where they will take the metal and roll it under these big high pressure rollers and flatten it out into flat sheets. And all of that changes the physical structure of the steel and makes it so that it has characteristics that are more usable. And then another process that's used, sometimes the hardening process of the hammering or the stamping is all that's needed. But there are times where, like with blacksmithing, that after you've pounded it and shaped it and created this physical structure in the elements inside the steel and hardened it, then you will heat it up really hot to about 725 degrees, 727 degrees Celsius, and it'll have a red hot glow, and then you quench it. And a lot of people think that that's tempering, but we're going to learn the real meaning of what tempering is. That's quenching. Quenching can be done in water, but it cools it really, really fast, which will make the outside shrink really fast, and it makes it really, really hard, but it's also kind of brittle. And so for most knives and things like that, they'll quench in an oil where it doesn't cool quite as fast. And because it doesn't cool quite as fast, it'll still be hard, but be a little bit more forgiving and less likely to shatter. Now, after you've quenched it, then there's another process that can be done that's called tempering. And tempering is where it gets reheated, this time to not quite as hot. It's in the 200 to 300 degree range in Celsius, and then you allow it to cool. And it's not as much like the annealing, because we didn't get it nearly as hot. Because with annealing, you actually almost got it to puddle. It was really hot. But this is still, keeps its shape. It's just 200 to 300 degrees Celsius. And then you allow it to cool. And that'll release a little bit of the stress from the hardening and the quenching. And then it makes it so that you have a really durable knife or an axe. If you're going to be hammering with an axe or a hammer, you want it to be hard because you don't want it to deform, but at the same time you don't want it to break either. And so it needs to be tempered. And then lastly, in our the studying of processes for making steel have different characteristics and hardness is something that's called surface hardening. And this is really important for certain types of things like gears, where they will take a lot of stress, but you don't want them to deform. And so they have to be tough and hard, but not break. And so they do a surface hardening where they'll heat it up with quite a bit of carbon, but the carbon's only allowed to get to the surface. And then they cool it And so the very edges of the metal will get really, really hard on gears or bearings where they have to take a lot of stress. But then the inner parts don't have near as much carbon, and so they're able to take and bend and take that stress without cracking and breaking. And on page 186, there's a picture of a gear system that's going together, and then right next to it's more of like a microscopic image, and it shows that the surface has that case hardening, or surface hardening as it's called, to make it tough and resilient and hard at the same time. So that finishes our first lesson, and we'll see how it goes from here. See you next time.